Hello and welcome back to my channel. We are at lecture number 5 now. So as I told you in the last class, we'll be doing the thermodynamics of cell. So let's begin with that now. We'll now start with the next topic, which is thermodynamics of cell. So here we'll be discussing a lot of concepts regarding how thermodynamics plays a role in working of a cell. So let's talk about it now. So before we start all these things, let me tell you a few of the things. What's the charge of one electron? What is the charge of one electron? So as we are aware, charge of one electron is 1.6 into 10 to the power minus 19 coulomb. So what's the charge of 1 mole of electron? Charge of 1 mole of electron will be 1.6 into 10 to the minus 19 coulomb times Avogadro number, right? Na. What's Na? Na is 1.6 into 10 to the minus 19 into 6.022 into 10 to the power 23. So these many coulombs. So if you multiply both the values, 1.6 and 6.022 on all these numbers, you should get it as 96500 coulomb. Are you familiar with this number? Yes. And what do we call this as? Charge of 1 mole is called as 1 Faraday. So from here we got that 1 Farad is nothing but 96500 coulomb. And this is what we will be requiring now. That's why I told you this now. So let's begin with the thermodynamics of it. Suppose it's a cell where we have the anode. See, maybe we can take the example of zinc sulfate in which zinc rod is dipped. And on the other side we have copper sulfate where copper rod is dipped. See, and now let's join them with a voltmeter. So as the electron flows, there will be electric current generated. Electricity will be generated, right? So what is the electrical energy we will get? So as the cell operates, there will be some electrical energy obtained. So how much will be the electrical energy? So we know the formula of electric energy is Q into V, where Q is the charge and V is the voltage, right? So as the cell operates, what's the voltage we will get? We'll get E in a cell or E naught cell if the cell is standard. So if it is standard cell, then we can call it as E naught cell. And what is the charge? Q into Ne. N is the number of moles. So number of moles into E, that means charge is going to be N into F for N number of moles. This is the charge for N moles of electrons flowing. So Q will be, and what is the voltage here? Voltage would be E naught cell. So from here, we got the electric energy as NF E naught cell. See, Q is NF and V is E naught cell. See, we got NF E naught cell. What is electric energy? This is the non-mechanical work done, right? This is the non-mechanical work done. And in thermodynamics, what do we call the non-mechanical work done as? Yes, you are correct. Useful work. So this is the useful work done. So how do we find our maximum work done? How do we find the useful work done? We find it using a very special term called as Gibbs free energy. Therefore, we can say that the useful work, is equals to delta G, right? And since the process is spontaneous, I'll call it as minus delta G. See, this electron flow happens spontaneously, right? So it will be minus delta G, right? See, this is the spontaneity, and that's equals to NF E naught cell. So from here, we got a very important relation, which is delta G naught. Since we're talking about standard cell, we'll make it as naught minus NF E naught cell. We get to a very, very important formula. Delta G is equals to minus NF E naught cell. This is for a standard cell. For normal cell, delta G will be equal to minus NF E cell. This is the delta G value. This is for any cell. We can use this. Not only cell, we can use it for electrodes also. That's how you can find the delta G naught and delta G. This is the first thing that we have learned. Now, So you can write this down. Let's go to the next part. For any electrode, for anything, suppose you want to study one particular electrode, or any electrode or any cell, whatever you want to study, you can write delta G as delta G naught plus RT ln Q. This is the formula that we are aware of. Yeah, this is the formula which we know already. Now, from this we can get a lot of relations. So what is actually delta G? See, what is delta G? Minus NF E naught cell. So if I want to apply this for cell, for any electrode or any cell, I can write like this: delta G cell will be equal to delta G naught cell is equals to RT ln Q. So instead of delta G, what can I write? Instead of delta G naught cell, we can write minus NF E naught cell. See, or E cell. Instead of delta G naught, what can I write? We can write minus NF E naught cell. Correct? Let's put both the values here in the main equation. Here, what will I get? I will get minus NF E cell is equals to minus NF E naught cell. See, plus RT ln Q. See, now I'll take minus on both the sides. I'll cancel NF. I'll get E naught E cell as E naught cell minus RT by NF ln Q. And does it look familiar to you? Yes, it is familiar. What is it? Nernst equation. Very good. It's Nernst equation. This is how Nernst equation is derived. Now let's look at some cases of Nernst equation. So this is how we can derive Nernst equation. Next, see some cases of Nernst equation. Case number 1. If case 1, case 1, for this Nernst equation we can have a variety of cases, right? You can use this equation also. So any of these can be used. Let's try to understand the thermodynamics here. So let's try to understand how it can be. For a spontaneous cell, we know that delta G of cell must be negative, right? So if delta G naught is nothing but, or delta G is nothing but minus NF E naught cell or E cell. So if delta G is negative, then minus NF E cell will be positive, because negative will cancel each other. So E cell comes out to be positive. That means for a spontaneous cell, that means if you want your cell to work spontaneously, then your delta G must be negative and E naught or E cell must be positive. Only then the cell will work on its own. Otherwise, it won't work on its own. We have to be aware of this particular point. Okay, this is one of the things that we must know. And yeah, this is the thing we must know about case 1. Case 2. If this reaction is non-spontaneous, if the process is non-spontaneous, how do you know that the process is going to be non-spontaneous? So for a non-spontaneous, delta G will be positive. We know that from thermodynamics class 11 chapter number 6. So delta G is actually equals to minus NF E naught cell, right? Or E cell. Since we're talking about delta G, we'll write delta G equals to NF E cell. So this will become positive since it is non-spontaneous, minus NF E cell. What can we say here? That for a non-spontaneous process, E cell is negative. So whenever you got E cell as negative, you have to understand that the process will not happen on its own, right? And the last case is case number 3, when the process is at equilibrium. The process is at equilibrium, and we know at equilibrium that delta G is zero, right? At equilibrium, we are aware that delta G is 0. So we will get delta G 0, meaning what will happen? Even NF E naught cell is 0. E cell is 0. That means E cell is also 0. Right? E cell is also 0. And if E cell is 0, then what will happen to equation number? What will happen to equation number 1? Equation 1 will become E cell. I'll write in the next page. In third case, it will become, since E cell is 0, it will become 0 is equals to E naught cell minus RT ln RT NF into log Q. And since it's equilibrium, Q becomes K. We know that, right? Q is at any time, but K is at equilibrium always. We know this from class 11th. This will become E naught cell is equals to 2.303 RT by NF log K. So this becomes very important formula for finding E naught cell and equilibrium constant. So K is equilibrium constant. So that's how both the things can be related. It's equilibrium constant. That's how both the term can be related. That's a very important formula that you've got. So we have got some few very important formula. So we'll summarize it, but before that, there's a quick graph that you must have to understand. Let's plot potential, electrode potential versus time, and see how how it looks like. Let's try to draw a graph. Okay, so here we are plotting a graph of potential versus time. So as we know, for Daniel cell, copper undergoes reduction and zinc undergoes oxidation. We are aware of it, right? We know it very well. So zinc will and become copper 2 plus. So copper, sorry, it will become copper. So copper definitely has a greater potential, right? That's why it is undergoing reduction. So copper has a higher potential. Zinc has a lower potential. So what will happen? Copper has a higher potential to reduce. Zinc 2 plus has lower potential to undergo reduction. So as the reaction progresses, copper will get consumed and consumed and consumed. Zinc will get formed and formed and formed. Zinc 2 plus ions. And there comes a point when, see, the E naught cell, when you try to find the E cell, that comes out to be 0. Why? Because the cathode anode, the copper concentration and zinc concentration becomes equal. And this point is called as point of equilibrium. Point of equilibrium. So after this point, the cell stops working. After this point, the cell stops working. That's the concept. After this point, the cell stops working. So what can we say on all these things? We can say in thermodynamics of cell, we must know what 1 Faraday means. 1 Faraday is nothing but the charge of 1 mole of electron. Then n moles will have n Faraday charge. Then I'd give an example of Daniel cell to explain the thermodynamics. So I told you that for any process where electric energy is coming out, the formula is Q into V. Q is NF and E naught cell is basically V. Then that is nothing but electrical energy, which is nothing but non-mechanical work done, because electrical energy is non-mechanical work done, which is also known as useful work done, which is also known as delta G naught. Now since the process is spontaneous, it becomes negative. So delta G is equals to minus NF E naught cell is the formula for standard cell. This is for any cell. And then we study that for any electrode or cell, we can write this thing. From here, I got this formula, which is nothing but Nernst equation. So we derived Nernst equation basically indirectly. And then I told you that if there are 3 cases possible, yeah. So there is a possibility of 3 cases. Case number 1 is when we have, a spontaneous cell. So for a spontaneous cell, the most important criteria is delta G negative, E naught cell positive. That's what makes a cell spontaneous. Whereas in the case of non-spontaneous cell, see, delta G will come out to be, negative. E naught cell negative, delta G positive for a small process to be non-spontaneous. And then we have equilibrium when delta G naught is 0. E naught cell is 0. And then we get this equation, which is very, very important for numericals, which is a relation between equilibrium constant. And then I have to explain how equilibrium is attained and how a cell stops working after a point. So let's summarize the things we discussed. I know I told you a lot of formula today, so let's summarize them at one place. So summary of this would be 1 Faraday is nothing but 96500 Coulomb, and this you have to understand that this is nothing but charge of this is nothing but charge of 1 mole of electrons. Very good, 1 mole of electrons. First point. Point number 2, we know that delta G, which is this frame, which is nothing but NF E cell. See, or delta G naught is nothing but minus NF E naught cell. And then we learned that for a spontaneous cell, for a cell to work spontaneously on its own, work spontaneously, what's the criteria? The criteria is delta G must be negative, which means E cell must be positive. Only then a particular cell will work. And then I told you that E naught cell is actually equals to 2.303 RT by NF log K. That's how the relation of E cell with K is. And then at the end we discussed about E naught cell 0 when the cell is at equilibrium. And here the cell stops working. The cell stops working. So these are the summary of the discussions we had up till now. So with this, we are done with the topic of thermodynamic treatment. So these are the main things that we had to learn about it, where I just majorly told you about the formula, how it is calculated, what are the important formula we have. And here I should tell you what N is. N is the number of electrons transferred. Number of electrons transferred. Now the next session will be all about using all these formula and whatever we have discussed since lecture 1 into doing questions that has been asked in previous year exams like NEET and JEE. We'll be solving them in the class and we'll learning how we can do it efficiently in less amount of time. So I hope this session was useful and you learned a lot about how thermodynamics plays a role while a cell works, right? So I hope this concept was clear. If you enjoyed this video and you learned something new, please like my video and subscribe my channel and share it to your friends. Thank you so much.